Okay, we are continuing our discussion of impedance and its relationship to transistor amps. We just have derived the input impedance for a simple transistor amp, and now I'm going to do the same thing for the output impedance. So here is my loop equation that I have established earlier. This essentially is the voltage following this loop around. And I've got my output voltage of my source. I've got the base current and the source resistance. So this piece here constitutes the input to the amplifier. The base emitter voltage drop between that point, and the emitter current that is, I'm assuming, flowing basically all the way through the load. I'm ignoring the current that might go through an emitter resistor that is connected in parallel with the load. So now my question is, what is Z out? So Z out, remember, is going to be defined by minus delta V out over delta I out. That's how I define the output impedance for these kinds of circuits. So I want to find this quantity here and this quantity here. I know from the way that I have set this up that I out is essentially equal to the emitter current. And I also know that the base current and the emitter current are related to each other by the following relationship. The base current is equal to the emitter current divided by 1 plus beta, where beta is the amplification factor. So now the main difference I'm going to specify here is I'm going to assume that V naught, that is the source voltage, is held constant. But I'm holding that constant while I make some change on the output. That is, I'm going to change the load, and in so doing cause a change in current going through the load and a change of voltage across the load in order to get V out versus I out in terms of their deltas. So I'm going to hold V naught constant, and I'm going to do the usual thing that I have done before, take some differences and see where that leads. So delta V naught is going to be equal to 0. That's going to be then followed by delta IB times RS and a delta VBE and a delta IE times RL. So this essentially here, this piece on the end, which the whole thing is equal to 0, this piece here represents the change in the output voltage, because the voltage that you see on the output is going to be given by delta IE times RL. So this is also delta V out. This term here goes to 0 by construction. This term here is related to the emitter current or output current by that relationship there. So I'm going to then rewrite this as follows. Minus delta IE divided by 1 plus beta times RS minus delta VBE minus delta V out is equal to 0. And I'm going to make the assumption that my emitter current is going all the way through the load, so that delta IE is the same as delta I out. So I would have minus delta I out times RS over 1 plus beta minus delta VBE is equal to delta V out. So now we go back to our results where first of all we're assuming that delta VBE is equal to 0. That is the simplest model. So simplest assumes that delta VBE is equal to 0, that is VBE is fixed, and I get that delta V out divided by delta I out, which is given right there, is going to be equal to minus the source resistance divided by 1 plus beta. So what you see is that the source resistance is actually decreased by the fact that the transistor can amplify the current. Now, this is the simplest model. It's the most important one. If we then assume our Ebers-Moll picture, which I will redo over here, so remember Ebers-Moll says that the collector current is equal to some constant times e to the VBE over VT, which is a physical constant. If I take a delta IC, that gives me a 1 over VT times IC, that is the same function over again, times delta VBE. And I'm calling this new quantity little re, or 1 over little re, times delta VBE. So that means that delta VBE is equal to little re times delta IC, which is pretty close to little re times delta IE. And I can write that as little re I can't do anything with that actually. So I'm going to put that back into here. Okay, this is also the same as delta I out. So I have then, under my new arrangement, delta minus delta I out times the quantity Rs over 1 plus beta plus little re is equal to delta V out. And then Z out, you can see by the similar construction as before, is now going to be equal to Rs over 1 plus beta plus a little extra, little re. So this Z out is not quite as good as we thought it was under our simplest model. It's up by a little bit. This is usually on the order of 25 to 50 ohms to 100 ohms, depending a little bit on the quiescent current. That is, it does depend on IC. And we add that to the resistance of the source divided by beta. And that's pretty much it for transistors.